Okay, let's get started. Our last class of the semester. And quiet. I got a big voice so I can amplify well. So today we're going to be talking about B-trees, which is yet another variation on balanced trees. And on the exam, there will be one problem with them, just like there is on the sample exam, and hopefully that's going to be the activity we do in class today so you get practice with it. Also want to say one thing about implementation of your AVL trees in the final lab. I want to point out our exam is in here a week from Friday, so that's a week from tomorrow at 10:15. And the exam will be an hour 15 minutes, not 2 hours. So it'll go from 10:15 to 11:30. It will not be cumulative, so it will be slightly cumulative. It will be since the material for spring break. So there is, on that, we have covered, since spring break, we've covered linked data structures, recursion, and trees. Now, with the linked data structures, the only thing that's going to be there is a short code fragment that has you somehow linking or delinking a node from a linked data structure like a queue or a doubly linked list or a singly linked list. I did not want to give you 3 problems for the coding portion of the exam, and therefore I decided to put a shorter code fragment, nothing along the lines of the queue problem from the sample coding exam, but something shorter. So you should review that problem. Also, someone pointed out that on some boxes, apparently the JavaScript window that comes up doesn't come up with a scroll bar for the solution to that queue problem, but you can always find solutions to the coding problems. Also, if you go to the exam section and you look at the final, I guess I didn't have solutions, but you have final coding questions, then the coding solutions are there in the solutions. So if you can't quite see the complete solution to the coding problem for queues, it's also there in the coding solutions. So questions about the paper exam next Friday? Any questions? Okay. Then a word about the implementation of the AVL tree lab, which is not due until actually Friday evening, technically Saturday morning. So you still have time to work on it. When you are rebalancing, so you have a tree. Let's say this is your tree. Okay, so this is an imbalanced AVL tree. And in order to rebalance it, you're eventually going to, well, I'm just going to put the heights here so you can see what's going on. 0, 1, 2, this is a 0. So the imbalance is eventually going to occur at this node. And you're going to be looking at all the nodes between the inserted node and this node right here. Okay? What I have seen in some of the labs that I have looked at is a complete recalculation of the height of a tree from scratch at each node. So first, check balance, what I see in check balance is some of you adding a new function called recursive height, which is not in the methods you have been given. So some of you are creating outside functions and you are recomputing, you're saying basically n height equals, and you recompute it recursively. Well, when you do that, you look at the entire subtree. So you start out and you recompute it here, and you look at the entire subtree. And then you try to do it here, and you look at the entire subtree. And you do it here, and you look at the entire subtree. And you do it here, and you look at the entire subtree. Well, by the time you get to the root, you're looking at all the nodes in the tree, which means you're looking at n nodes to recompute the height. So you've turned what was supposed to be an order log n operation into at least an order n operation because you're looking at all n nodes. And a quick look would suggest that because we're looking at n nodes total, and calling that recursive height function n, log n times, it's a quick look suggests that you've actually turned the insert operation into an n log n operation, which is much worse than if you just stored in a vector and performed the really slow insert of moving every item to the right. So when you do these kinds of operations, you need to be really careful that you don't do things that are computationally expensive. Okay, in this case, you can't afford to recompute the height of the entire subtree. It completely blows your running time out of the water. Okay, so that's why you were given a height variable. If you look at the lab, okay, one of the variables is height. And the idea is that you're always keeping these height variables up to date. And in particular, whenever you reach a node, any node, whatever it may be, you are guaranteed that the height variables of its two children are correct. First of all, the heights of the subtrees that were not changed, so the height of this subtree was not changed, the height of this subtree, all the heights of trees that are not on the path from the leaf to the root, their heights cannot have changed. So they're clearly up to date. And it turns out the only nodes whose heights can change are exactly those nodes that you traverse on the path from the leaf to the root. So I can write that down. The only nodes whose height can change is nodes on the path from the inserted node, or if it's a deleted node, the parent, to the root. And you are updating, as you go to each node, or traverse to each node, you're updating its height. So by the time you get to a node like this, you're guaranteed that the nodes below it have had their heights updated. So instead of recursively calling the call to height, all you have to do is say that your height is equal to the max of your left subtree height, right height, plus 1. You already have those heights, and they're already correctly computed, so there's no reason to go beyond that. And that's an order 1 operation to do, as opposed to an order n. Okay, so that's what I expect you to do in your AVL lab. I don't expect you to be calling a recursive height function that recomputes the entire height of the tree from scratch, because that will just blow your running time out of the water. Okay, now, next semester, many of you will be taking 311, discrete math. And the reason you take that is because the math there, or in computer science, is often different than the math that you've been learning in calculus. Okay? So actually, after I sent that post last night, I thought, let's look more carefully at what the actual cost of the operation would be if you recomputed the height from scratch every time. Okay? And it turned out that it wasn't as bad as n log n. The reason is that if the tree is balanced, the number of nodes in the left subtree is only n divided by 2, or roughly n divided by 2. The number in either of its subtrees is roughly n divided by 4, and so on. And so what you are effectively looking at when you recompute the height is at the leaf has no children, so it's 1, plus the next one up is looking at only one leaf, or potentially 2 leaves. It could have something over there. And in general, if you're thinking about it, it's going to be dot dot plus n divided by 8 plus n divided by 4 plus n divided by 2, plus the last one looks at n nodes. So the number of nodes, the last one at the root, you're looking at n nodes to compute the height. At the next to last level, you're looking at n divided by 2, then at n divided by 4. So actually you're looking at a sequence that looks like this. And does anyone know what this sum is equal to? This is something you may well learn in 311. Nope, this one is not n times n divided by 2. It's not that bad. Well, believe it or not, this sum right here is n minus 1. It's actually, the result of this is 2n minus 1. Okay, so if you think, let's do an actual example. 1, because you're having each time 1 plus 2 plus 4, that's 7. What's the next number in the sequence? If you're doubling every time. 8. Okay, so that sum is, so if we now, that sum is what? 15. What's the next number in the sequence? 16. Okay, so 15 and 16 is 31. What's the next number in the sequence? So you see, if you're actually adding, if you're always dividing by 2, and adding that sequence, the actual addition of all the numbers beneath n is actually n minus 1. Okay, this is the kind of thing, the reason you learn this kind of math in 311 is because computing these kinds of time bounds is important. Okay, it turns out that recomputing the height every time from scratch is going to take you not order n log n, but order n. It's still bad, but these kinds of things are important as tools when you become programmers in the real world, because efficiency really is a big deal, and being able to analyze the running times of algorithms is a big deal. And so being able to do this kind of math, 0 plus 2 plus 4 plus n divided by 8 plus, and knowing what these sums really are is important, because it really does affect running times. Okay, this turned out to be order n, not order n log n. That's a big difference. Okay, so in 311, a lot of times when you're sitting there doing the math, you may wonder, why do we learn all this kind of math? The reason is it really helps you when you are trying to compute the running times of these kinds of algorithms. Okay? So I'm not going to test you on this, but I just wanted to give you a taste of why CS311 discrete math is fairly important and why it's different than calculus. Just like that other summation I did the other day where I was summing 1 plus 2 plus 3 plus 4 plus n minus 3 plus n minus 2 plus n minus 1, which was the sum essentially from I equal 1 to n minus 1 of I. Again, most of you didn't know what that sequence summed to because you're not learning it in calculus. Yet that's an important sum in computer science because it gives you the running time or the number of loop iterations for many loops. Okay. Second thing. Last time I said that figuring out the running times of recursion is a little different than anything else. So for example, when you had that find function that you wrote for binary search, okay, actually let's just take a look at it. Okay, so here is the code for doing a recursive find of a key in a binary tree. And you see some if statements and you see some sequentialness. So basically, based on what we said, this if statement takes 2 instructions. Why does it take 2 instructions? Maybe I will make you do this on the exam. Why is that 2 instructions? Dave, I'm going to put you on the spot.
Okay. So the 2 instructions on that 1 line.
They're 2 time units. 2 time units.
Okay.
This is taking 2 time units, not 2 instructions, 2 time units.
Okay.
What are the 2 time units?
Evaluation of the if statement.
Very good. So the evaluation of this conditional.
And then just returning a value.
And returning the value. So this costs you 1 time unit, this costs you 1 time unit. So it's the maximum of the cost of evaluating the if plus the maximum of your true branch, which is 1, and your else branch, there's no else branch, so that's 0. So that's 2 time units. Okay? So the same thing for this one. It's 2 time units. 1 for the comparison, 1 for the return statement. Okay? Now, this is the real head scratcher. So here we have 1 for the comparison, and then it's the max of this recursive find and that recursive find. Well, that's kind of a pain in the neck. Okay, so we have essentially that our t of n for this function is equal to, we always execute, or almost always in the worst case, execute these first 2. And that's 4 instructions. And we always, in the worst case, execute this statement, but these 2 recursive calls are a pain in the neck. What we do know about them is that in general, if the tree is balanced, how many nodes, if the tree is balanced, so if the tree is balanced, and we search the left subtree, how many nodes do we expect to be searching? Or how many nodes in the left subtree? Not log n. It's a nice guess. N over 2. So if there's n nodes in the entire tree, then, and it's balanced, there's roughly n divided by 2 in each of the two subtrees. Because they're roughly split between the two subtrees. Okay? So that means that the size of this problem, it's a recursive call, right? So T of n is really equal to each of these function calls is being done with half of the nodes in the tree. So effectively, it is the max of T of n divided by 2 and T of n divided by 2 because it's a recursive call with half the nodes. So effectively, it's 5 plus whatever T of n divided by 2 is. That's what's called, so this is called so what we have is T of n is equal to roughly 5 plus T of n divided by 2. This is called a recurrence relation. Notice kind of the notion of recursion that's embedded in that. I'm not going to prove to you what the solution to this recurrence is. Again, in CS 311, they should take up this notion of recurrence relations. Does anyone know what the solution to this recurrence relation is? Has anyone ever seen it? It's okay if you haven't. So T of n equals 5 plus T of n divided by 2. There's a so-called closed form solution to it. You can actually, just like before, I kind of had where I was writing n plus n divided by 2 plus n divided by 4 plus n divided by 8. And that had a closed form solution. It was actually n plus n minus 1 equals 2n plus 1. So I was actually able to take that sequence and break it down. Okay, this actually has the same flavor to it. If I was to keep writing it out, I would get 5 plus T of n divided by 4. So I could keep writing that out and I'd get a whole bunch of 5s. The question is, how many 5s am I going to end up with? So it's a good guess, Dave. It's not n. Yeah, log n is what?
Yeah, you get like 2n plus 5 log n something.
Yep, you come out to something. I'm just going to write in it's approximately 5 log n is the closed form solution. Roughly. There's roughly log n of those. Why? Because when you divide n by 2 every time, you get down to 1 in about log n times. So you're going to add up 5 about log n times, and then in that final call where t is equal to 1, it's either it's one of these two cases, so you come up with a little less than 5. But again, that's when you do recursion, you end up with a recurrence relation like this, and there are solutions to those recurrence relations. Okay? So you should be learning something about that in 311, I hope. Okay, I will not ask you to evaluate these kinds of recurrence relations on the exam. It's beyond the scope of this course because you don't yet have the mathematical basis for doing that. But I at least wanted to show it to you. So questions? Okay. So you actually did learn two new sequences if you ever see them. You know that n plus n divided by 2 plus n divided by 4 plus n divided by 8 is really 2n minus 1. And you know that t of n equals 5 plus t of n divided by 2 is really the constant times log of n, roughly. Okay. Clear all that out of the memory bed registers. And let's move on to B-trees. So far we have been dealing with binary search trees, which have just two leaves, or two children, at most two children. And if we have n nodes and a balanced tree, then that is going to be equal to log n levels, which means that we will search that many levels potentially to find a key. So one might say, gee, that sounds nice, but we could reduce the number of levels. How could we reduce the number of levels? Because if we're going to have to search once at each level, it seems like it'd be nice if we could reduce the number of levels. So how could we reduce the number of levels? Increase the number of children. If we could have more children, whoopee! Lots of children. Then not nearly so many levels. Okay? So, if we had, for example, m children, up to m children per level, it turns out that it would be log mn levels, which could be somewhat smaller. Like if you had 10 million people, like I think Florida has roughly 10 million people with driver's licenses. So log 2 of that is going to be much greater than, say, log 100 of that. And I didn't do the logarithms before I came here, but I do know that it is about, let's see, to the fifth. It's roughly 7 times greater. So if we could increase the number of levels, that would be swell. Okay? What might be a drawback of increasing the number of levels? Oops, yeah, question.
Yeah, my question was, isn't the whole point of binary trees that, like, there's only three because you can just check whether it's good or not?
Bingo. So I was going to say, what is the disadvantage of going to so many nodes? And you just nailed it. So what's going to happen, instead of being either or, how many nodes must I potentially search each time? M. Oops. So it goes, the problem is with a binary search tree, let's see, I wish I had done this computation, but it was the spur of the moment. So let's see, for 10 million, 100 times 100 is 10,000. Times 100 is a million. So it's roughly, we'll say 4. So that's roughly 4. So we'll say this is roughly 25. So the deal is that this one may have to search up to 4 m nodes, which is 4 times 100. This one the binary search tree may have to search up to, let's see, 25 times more. So 25 times essentially one comparison. So it only searches one node. So this does, even though it's only 4 levels, it may have to search 100 nodes at each level, so 400 nodes. Here, we only have to search one node at each level, but we have 25 levels, so we end up with 25. So it turns out that bigger isn't actually better, okay? Because even though you reduce the number of levels, you end up having to search, it's more like linear search at each level. Okay, so the question would be, why would we ever consider going out to these enormous branching factors? So we often talk about these as branching factors. Why would we ever consider having such an enormous number of children when you have to look at so many of them? Well, for in-memory, what we call in-memory searches, where we are just looking at random access memory, the answer is never. We always are going to prefer binary search trees. That's not the only kind of memory. What other kind of memory is out there that's a lot slower? Pardon? Come on. Secondary memory is a lot slower. Okay? And I bet at least in 130, didn't you talk a little bit about how much slower it is to read something off of a disk than it is to access something in memory? Okay, so here's the deal. If we're now out on a disk and we have to read one of these nodes, now it's on a disk. Okay, so reading one of these 25 nodes now might take a number of milliseconds. It's no longer microseconds or nanoseconds, now it's up to milliseconds. That's huge, okay? Because if it takes several milliseconds to read this, now, let's now do some more calculations. So we had 4 in the 100 child case. And this was the 2-child case. So we had 4 levels, but 100 children to be searched per level. Here we had, say, 25 levels, but only 1 child to search per level. So we concluded it's no good for in-memory. But let's say that we're now looking at secondary storage, and let's say that it takes 2 milliseconds to bring something to read a node into memory. Okay? So 8 milliseconds for the B tree, and 100 or 50 milliseconds for the binary search tree. Now, how long is it going to take to search 100 children in the node? Because now we're in memory. Pretty fast, huh? CPUs are pretty fast. Probably on the order of nanoseconds. Not milliseconds, not microseconds. Even if it's 1 microsecond, which I can't do very well, 1 microsecond. Okay, and this is 100 times faster, so it's 1/100th microsecond, which is faster overall in the scheme of things. The top one, because it took basically 8 milliseconds. The microseconds used for doing the search of the children was noise, right? This is kind of like big O analysis where we look at the biggest factor. The biggest factor here is the disk read. The disk read totally swamps the cost of searching the children. So if we're in secondary memory, now the real concern is the number of levels because that's going to dictate the number of disk reads. So in secondary memory, okay, cost is determined by the number of disk reads. Okay, and that means we want to, which means we very much want to minimize the number of tree levels. So while B trees never make sense in random access memory, B trees are the workhorse for secondary memory, it turns out. So databases, Google, Uber, Amazon, they're all basically using B trees to store all that credit card information, or the Florida Driver's License Bureau is using it to store people's driver's licenses. So in secondary memory, B trees are the way to go. So B trees, basically coming back to this idea, are balanced trees, but they can have up to m children. Okay, so a B tree is a balanced tree with up to m children. So that is called an M order. You often hear the words M order tree. M determines it. Okay, so if you can have m children, what that means, let's actually look at some examples now. Okay, so here is an example of a B tree of what order based on what I just told you. It has a maximum of 4 children. So the order is 4. So if you have 4 children, what does it look like is the maximum number of keys you can have per node? So if you have a M order tree, can have a max I'm sorry, not children, keys. So in this case, how many, with 4 children, what does it look like is the maximum number of keys? 3? So in fact, that's the right answer. So generalizing, an M-order tree can generally have a max of n-1. Very good, Dave. Maximum of n-1 keys per node. So you keep the keys in sorted order in the nodes. So EKP, or down here QTW. You keep them in sorted order. And it still has the same property for any key. All keys in its left subtree are less than it, and all keys in the right subtree are greater than it. And we're again not going to worry about duplicates. Okay, so basically if we have the key, it's greater than all keys in the left subtree. So in the left subtree, it's greater than all the keys. And in its right subtree, it's less than all of the keys. So it's the same idea that you had with binary search trees, but now you have multiple children. But if you look, for example, at T, right here. In its left subtree are the keys R and S. They're both less than T. In its right subtree is X. Well, actually, there is no right subtree right now for T. It's only W that has one. So, but basically, any tree to the left of T is going to have keys less than T. Any tree to the right of T is going to have keys greater than T. So the find algorithm is very simple. Okay, you start at the root. Let's say I'm looking for Y. I'm going to go through and ask I'm going to do a linear search through the root. So find a key starting with a node. Basically, we are going to say while, or let's do it this way. Let's say for each K, which stands for key in node, if the key is equal to K, we will return the value. Okay, so that's an easy case. Okay. Then we're also checking to see whether the key is still less than it. So if we're looking for, in this case, Y is greater than E, it's greater than K, and it's greater than P. So in the end, you can see it's going to have to follow down to this node. And again, we would do our comparison with each key. So Y is greater than Q, greater than T, and greater than W. So we come down here, and we would actually eventually find Y. Okay, so let's do another example. Let's add something. Let's add a couple more nodes. So let's add L. So add L here. So if we're searching for L is greater than E, greater than K, but it's less than P. So when it's less than P, we're going to go to P's left child. It's got to be in the left subtree. And it is less than M, so we come down here and we find it. So it would appear that we're going to keep going until what condition is met? At what point are we going to follow a link down to a subtree? If it's less than. So if the key that we're looking for is less than K, then we follow, or we call find, we return find of key on K's left subtree. Okay, what happens if we fall out of the loop? We get all the way to the end of the loop and we have never found a K which is greater than our search key. What do we know? We go down the right one. So now we'd have to do one final check here, okay? So the check would be if the node is a leaf, what happens if the node is a leaf? What does it mean if we haven't found the key? It doesn't exist. So if node is a leaf, we actually return null because key wasn't in the tree. Else, we're going to return find of the key on k's right, or actually on the rightmost, find key on the rightmost subtree for node. So if we fall out of that loop and we're still at an internal node, we're going to return the result of going find on the rightmost subtree for the node. Okay, so this isn't all that much different from doing a search of a binary search tree. We're just doing a linear, so with a binary search tree, if the search key was less than the node, we went left. Otherwise, we went right. It's kind of the same thing here. We look at the search key and we ask if it's less than E. If it's less than E, we go left. If it's greater than E, we effectively go right to the next key. And we repeat the comparison. Okay, so a balanced tree isn't so much different than a binary search tree in how we do find. So any questions about that? Okay, the key is keeping this puppy balanced. Okay, so through inserts and deletes, we need to keep it balanced. So this one back here wasn't actually a very legitimate B tree because there are some conditions. So we basically put a balance conditions on B trees. Balance condition. So the first balance condition is that all all nodes have greater than or equal to m divided by 2 keys. And again, if you haven't seen it before with the arms on top, this is the ceiling function. So I believe it's m divided by 2, maybe minus 1. It's 5, yes, 5. It's 4, no, I believe it is this. It's greater than or equal to m divided by 2. And the second condition is that the the leaf nodes are all at the same level. That's not the case with binary search trees. So here you noticed the leaves are all at the same level. With a binary search tree, you could have K, B, M, L, and the leaves aren't at the same level. But that's not the case with a B tree. They're all at the same level. So that's the balance condition. All nodes have greater than or equal to m divided by 2 keys. There's one exception, and you can see that exception here in the diagram on the left. There is one node here that does not, this is a B tree of order 5, yet there is one node, yes, so this is actually a minus 1 because I was taking the ceiling. So this is, sorry, put a minus 1 right here. The very end, put a m divided by 2 ceiling. I'm taking the ceiling, so that should be minus 1. So this is a tree of order 5. 5 divided by 2, the ceiling is 3. Minus 1 is 2. You can see that there are some nodes with just 2 children. There's one exception. What node here has fewer than 2 children? The root. So the root is allowed to have as few as one child, or to have as few as one key, which means 2 children. Okay? So, there's a number of cases for doing insert. The easiest case is when we insert into a node that is not yet full. So in this case, where we have a B tree of order 5, what is the maximum number of keys that we can put into any node? 4. So none of these is even close to being full. So no matter what key we insert next, there's going to be room for it. Okay? So that's a nice case. So let's see here. And so here they're starting with a very simple B tree and they're going to build it up from scratch. So initially, they're working through an example and they're saying, let's insert these keys right here. So initially, the root node is just the leaf node. When you insert C and G and A, you get, when you sort them, these 4, and they can all be accommodated in the root node. When I insert H, that's my first issue, because now the node is full. So when I insert H, what happens is I am going to promote the middle key. And I'm going to split this node in half. So what happens is I'm going to split this node in half. So keys A and C come down to here. So here, keys A and C, they come down to here. Keys G and N, well, actually, that's not true. I'm adding H. So H would go right there. So keys H and N come into the right tray, and G gets promoted to become a new root. So here we created 2 new nodes, a root node and a second leaf. Okay, and we promote it the middle key. Okay, so carrying on, we next insert E, K, and Q, and there's no problems. So E is going to go into this tray. Where is K going to go? To the right, because it's greater than G, so down here. Q is also greater than G, so it's going to end up down here. See if you can do this. Inserting M is going to require a split. So C, just take a moment. See if you can do this yourself. Try to insert M into this tree. See if you can figure out what the next, how the tree is going to look after M goes in. Okay, what do we got? What do we think? Dave?
I believe we eventually promote H and put it up into the root so we can
Okay, so we put M. So what you want to do is promote H, and then there's room for M, right? Okay. So then the thing is, I need to have 3 children, but I still only have 2 children. I promoted H, so if I have G and H, I actually need to, at this point, have 3 children. I guess maybe I didn't tell you that, but every node has to have a left and right child effectively. Whoops, that wasn't the way I wanted to do it. I can't actually promote H because, and leave it with just, and fit M in there because I still have only 2 children. Yes.
Wouldn't you just split the right tree into two and put M there?
Very good. So I'm going to split the right tree in 2.
Make M the right child G and then have the H be the left child M and M be the right child M?
Yes. So what's going to happen is when I put M here, it's too big. So what I need to do is split it. I'm going to split it in 2, and because M is in the middle, M will get the promotion. H and K will go off to their separate leaf, and N and Q will go to their separate leaf. Okay, so basically, when you insert into a full node, okay, so when inserting into a full node, or inserting into a full leaf, okay, 1, promote the middle key from this leaf. And that includes, so I'm going to say overloaded leaf. So I want to make it clear that, in effect, when you consider what is the middle key, that includes the inserted key. Because in this case, M was the inserted key, and it was the thing receiving the promotion because it was the middle key. And then split the leaf into 2 leaf nodes and move the lower half to 1 node and upper half to the other node. Now in reality, one of the nodes already exists, so you actually only move half of them, and half of them remain. Okay? Make the promoted point to these 2 nodes. So you can see here, M, in effect, its left subtree is H and K, its right subtree is N and Q. Now notice that 2 keys share a child. So G's right child is M's left child. Okay, so you kind of do have a sharing of children in some sense. Okay, questions about that? Okay, so you insert F, W, L, and T, and you can get F, whoops. So I can get F's less than G, it goes into this leaf. W is going to go into this leaf. L is going to go into this leaf because L is less than M. And T is going to go into M's right, is going to go here. So after we insert these 4 letters, we have the tree that you see right here. Okay? Take another crack at it. Now we're going to insert Z. We're inserting Z into this tree. By the way, on an exam, you're never going to get to insert F, W, L, and T into the tree. Sorry. The question is always going to be when you're inserting into a full node. So Z is next. We're inserting Z. Michael, I'm going to let you do it. What?
It looks like we put Z at the very bottom right-hand corner.
Very good. So Z down here.
P would be the middle.
Very good.
Promoted.
Promotion. You're right.
And I don't know what it is.
Okay, so we said that the lower two, then someone help him out. What happens after T gets the promotion?
Right one split.
Right, we split. So N and Q go off on their own, and W and Z go off on their own. Okay, so what happens is, as Michael said, T gets the promotion up here, N and Q off to their N and Q, lower half, W and Z, upper half. They each go into their own 2 nodes. Okay? Now, we're going to skip ahead in our story, make it more loaded. There we go. So we get to this big puppy, and we're going to add S. Okay, so S is less than T, so we're going to come down to here and try to put S into this one. So what gets the promotion? Q gets a promotion, but what's the issue with the promotion? It's full as well, so what do you think happens? M gets the promotion and Q and T come off on their own. So I can't fit it all, but first of all, at the very bottom, adding S, NP and RS are going to end up in separate nodes. So down here, NP and RS, but that's going to cause Q to get promoted, and that's going to overload this internal node. So it's going to split, and when that internal node splits, you can see it here. This internal node is here. It splits this way. So M gets the promotion. Q came up, so Q and T come here, D and G down to there. And then further down, NP and RS were also split. So you could end up having to split, in the worst case, all the way up to the root, although that's pretty rare. So any questions about insertion? I don't think it's all that difficult once you get a few reps. We okay with it? Okay. Deletion is a little bit trickier. So first of all, as it may not surprise you, deleting from a node that has more than the minimum is the best case. So if I delete X, that's really easy because I can just delete it and it's still, the leaf has more than the minimum number of keys. So the first case, is the easiest, where we delete something that is from a leaf that has more than the minimum number of keys. So it gets more interesting when we delete something that is in a leaf that is already at a minimum. I see they want to delete T. I don't want to consider an internal node yet. Let's go and find where they're deleting from a leaf. There we go. So here's our tree, and we want to delete R. The problem is R is in a leaf that when we delete it will no longer have enough keys. Okay? So what we try to do is see whether we can filch or take a node or a key from a leaf that has more than the minimum number. So we look left, and that leaf cannot spare a key. So we're deleting R, and if we look left, it can't spare a key. Okay, because it's a minimum of 2 keys. Remember, we are working with a tree of order 5. So in a tree of order 5, okay, it's every node must have a minimum of 2 keys, so we can't borrow from here. Can we take a node from its right sibling? Yes. So now comes an operation that almost looks a little bit like a rotation. Okay, we can't just dump X over here. We can't just say, okay, I'll take X and we'll make this S and X. Why can't we just take X and move it over here? Very good. It's not, X is greater than W, so if we just move X over here, it's not in the right tree anymore. So we can't just move X over, but what we can do is we can demote W. So what we can do is we'll delete R, we will demote W, moving it down here, and what do you think happens to X? It gets the big promotion. So it looks a little bit like a rotation, right? Because X is swinging up while W is swinging down. Okay, so when deleting from a leaf, if the leaf no longer has the minimum number of keys, try to take one from either the left or right sibling. So we always look left first. Okay? So if we can, the key from the sibling is promoted, and a key from the parent is demoted to this leaf. And the reason I'm being a little vague about which key gets promoted and which key gets demoted is it all depends on whether the key comes from the left sibling or the right sibling. Okay, if we had been able to take one from the left sibling, we would have been taking the last one, which was P, so it would have gotten the promotion and Q would have gotten the demotion. So it all depends. If we're taking from the left sibling, we're going to take the greatest child out of the left sibling. And if we take from the right sibling, we're going to take which child from the right sibling? Least. Because we can promote the least one from the right sibling, and everything in the right node will still be less than it, and everything in the left one will be still less than it. So we take the least key from the right sibling. Okay, so sometimes that's not an option. What happens if we delete from a leaf? Let's delete E, and when we try to borrow, we can't borrow. So we look left, but there's nothing to borrow from the left sibling because it's at its minimum. We look right, but we can't borrow from the right sibling because it's at its minimum. So this is problematic. What we have to do is we need to merge two leaves at this point. Okay? And if possible, we merge with our left sibling. If we have a left sibling, we're going to merge with it. Okay, let's make sure that's what they're doing because you can go either way. Yes. So they're merging with the left sibling. So we merge these two leaves. When we merge them, we also have to remove D from the parent and move it down into this new leaf because we have consolidated two leaves. And in consolidating two leaves, we've reduced the number of children. So the number of children here has gone from 3 down to 2. So we can only have one key left here. Okay, so we delete it. Let's see if they... What's the issue with... So we deleted it and D came down. So D is down here and E is gone. What's the issue right here? Only one key. It has to have two. So what do you think we do? Bingo. We look left, nothing's there. We look right, can we borrow? Please, can we borrow a dime? Nope. Why can't we borrow from the right? It's already at a minimum, and it would leave it with only one key. So what we have to do is merge. So we're going to merge this node, and what do you think happens in that merger? Good. What you're showing me, but very good. So these three actually end up merging. It's a three-way merger. So when we're done, it's G, M, Q, and X all together. The last case we want to consider is what happens when we delete from an internal node. That was actually the first case considered in the notes. So here's a B tree, and let's say that we decide to delete the key T. As you can see, T is a key in an internal node. What we do in this case is find the smallest key in T's right subtree. So in that case, it's W. And we're actually going to delete W from the tree, and then we're going to replace T with W. And that's going to always be our strategy with deletion from an internal node, is we're actually going to find the smallest key in the deleted keys right subtree, we're going to then delete that smallest key and replace the deleted internal node key with that smallest key. So in this case, we're going to replace T with W. And this would be a particularly easy deletion because the leaf node that contains W can lose a key without going below its minimum. So in effect, W just gets promoted up and it replaces T. And notice that by using the smallest key in T's right subtree, we're going to maintain the order because that all values in the left subtree are still going to be less than W because W is greater than T. And because W was the smallest key in T's right subtree, everything else that remains in that subtree is greater than W. So it's okay to promote W to replace T. Okay, now let's do another example where we try to delete C. So the smallest key in C's right subtree is D. So we're going to delete D, but as you can see, what happens is it cannot borrow a key from either its left sibling or its right sibling because it's a tree of order 5, so we have to have at least 2 keys in every leaf. So we're going to have to merge the node containing AB with the node containing E. Remember that D has been deleted. Actually, D has not been deleted, it's being promoted up here to C. So, but the point is we'd have a node with A, B, and E. Okay, so that's kind of, you see this condition, we've deleted D, we put D, D has replaced C, D is right here, has replaced C, but now E is by itself, so we have to merge A, B, and E, and remember when we do that merger, we have to bring down D. So here we go, A, B, D, and E, they're all combined in one node, and F is now pointing to these 2 subtrees. The problem is F is now the only key in that internal node, and that's not enough. However, we can borrow M from its right sibling. If you remember what to do in this case, we are going to promote M up to J, to the root, and J is going to come down and join F. And so that's going to give us our final rebalanced tree. M has come up to here, and you can see J has come down to join F. And in addition to that, you can see that this subtree KL has kind of moved over, if you will, to the left side. Here it was in the right side of the tree. Down here, it has moved over to the left side of the tree. So when we moved J down, J had to take over pointing to this KL subtree. So that does it for deletion. The last thing we need to consider is how you choose M. Okay, so if you have so let's just quickly. So how do we choose M for a B tree? Remember, M is the maximum number of children. Okay, so remember we're using B trees for disk storage, and it turns out that on disk we store, so on disk we store data in blocks. For Unix, the blocks are 4096 bytes. So what we're going to do is choose to store as many key pointers or as many key values into value pairs as we can into these blocks. So basically, we're going to choose M to be the maximum number of key value pairs we can fit into a block. So we choose M to be the maximum number of key value pairs that we can fit into a block, because essentially we want M to be as big as possible to reduce the number of levels and hence reduce the number of disk accesses. That does it for B trees.